In the last 48 hours, a weakening storm built Japan's worst flood threat in years. In 2018, a weaker typhoon than this one killed 225 people after it weakened. Every network is tracking the storm. Nobody is tracking what the storm is feeding. There is a name for what is happening right now. It has been in the science for years. By the end of this, you will know what that name is. Stay with me. In July 2018, a typhoon moved through Japan. It was not the strongest storm of that year. It had already begun to weaken when the worst began. By the time it was over, 225 people were dead. 2 million people had been pushed from their homes. 15 prefectures recorded damage. The property losses reached nearly $10 billion. The storm's winds did not cause that. Something the storm activated on its way through caused it. That same thing is active right now over Japan. I want you to hold those two facts side by side as we work through this. A storm that was weakening, a death toll that was still climbing. That gap between what the storm was doing and what the country was suffering is the entire reason this video exists. The gap has a mechanism. The mechanism has a name. And the same mechanism is active over the same country right now, in the first week of June 2026, while a typhoon called Jangmi pulls away from its point of closest approach. The Japan Meteorological Agency issued its most urgent flood warnings on June 2nd, while Jangmi was losing power and moving away from its point of peak impact. That is not how storm warnings are supposed to work. Warnings escalate as storms intensify, then ease as storms weaken. The JMAR did the opposite. And buried inside the technical language of their own advisory was a sentence that explains exactly why. The agency noted that rain would begin falling before the typhoon center even arrived, driven by a stationary front sitting north of the storm. A separate system. Already loaded. Already delivering rain to western Japan, while Jangmi was still hundreds of kilometers to the south. The storm is not the threat. I am going to repeat that one more time so it lands the way it needs to land. The storm is not the threat. The threat is what the storm is feeding from a distance, and that thing has been positioned over Japan for weeks, soaking the ground, waiting for an injection of warm tropical moisture that Jangmi is now delivering from below. Subscribe to Rupture, because the Japan Meteorological Agency is releasing its post-landfall damage numbers right now, and we will be tracking every confirmed total as they come in. You will want to be here when it does. You will want to be here when it does. Now let's get into it. Part 1. What is happening? We start with the confirmed data on the ground right now, what Jangmi actually measured, where American military bases stand, and the first sign in the official record that something about the timing does not add up. The Joint Typhoon Warning Center, the United States military's tropical storm monitoring agency based in Pearl Harbor, Hawaii, placed Jangmi 107 kilometers south-southwest of Kadena Air Base at peak intensity. That is not a near-miss distance. That is a direct impact distance. Kadena is the largest American airbase in Asia, and while that base was battening down for the storm's closest pass, the Japan Meteorological Agency was simultaneously preparing language it would not issue until the storm had already begun to weaken. Let me show you what I am looking at. I have the Joint Typhoon Warning Center Bulletin pulled up. The agency goes by an acronym you will hear in this video, JTWC, that stands for the Joint Typhoon Warning Center. It is the United States Navy and Air Force unit that tracks every tropical system in the Western Pacific. Their bulletin from June 1st places Jangmi's center 107 kilometers south-southwest of Kadena. For an island the size of Okinawa, that is a direct hit on the southern half. The eye wall, the ring of strongest winds around the storm center, scraped across the most heavily populated part of the prefecture. American military families woke up to a wall of weather they had not seen on that island in nearly 3 years. Now look at what the Japan Meteorological Agency was measuring at the same moment. The full name is the Japan Meteorological Agency. Throughout this video, I will use the acronym JMAR. They are the primary forecasting body for the entire country. The JMAR recorded a central pressure of 975 hectopascals at Okinawa on June 1st. Hectopascals are the unit meteorologists use to measure atmospheric pressure at a storm centre. Lower numbers mean more energy, a tighter, more powerful circulation. At 975, Jangmi was at the upper edge of tropical storm strength, pushing into Category 1 typhoon range. Peak gusts at the Okinawa observation site reached 162 km per hour. In American measurements, that is roughly 100 miles per hour. The kind of gust that strips roof tiles, snaps power poles, and turns loose objects into projectiles. The JTWC's wave height data for the peak window reached 10.7 meters. That is 35 feet. The translation is concrete. Picture a wall of water as tall as a three-story building, moving toward the Okinawan coastline at full speed. Fishing fleets had been recalled. Container shipping had been rerouted. The ports were closed. The waves were not hitting empty water. They were hitting harbour walls, breakwaters, and the lower edges of coastal road systems that have been engineered to handle exactly this kind of event. The engineering held in most places. That is the only reason the casualty numbers from the wind and surge phase stayed low. This was the first major storm to hit Okinawa in nearly 3 years. The island sits in the typhoon belt. Storms passing within 300 kilometers happen multiple times every season. Direct hits at this intensity are rarer. The local infrastructure had a long enough gap that the muscle memory of a full lockdown had to be relearned in some communities. Every flight at Naha International Airport was halted. The Okinawa urban monorail stopped running. All major retail closed. Convenience stores, the backbone of daily life in Japanese cities, locked their doors. The island shut down in a way that residents under 50 had only seen a handful of times in their working lives. The United States bases on Okinawa entered tropical cyclone condition of Readiness 1 emergency. The military uses that classification when destructive winds of 58 miles per hour or greater are occurring or imminent. It is the highest readiness level a base can declare for a storm. All personnel are sheltered. All non-essential movement stops. Aircraft are tied down or moved to hangars. Vehicles are secured. The base becomes a closed system, riding out the storm until conditions allow personnel to emerge and assess. Picture a crew chief at Kadena Air Base, walking the flight line in the final hours before the storm made its closest pass. She has run this checklist before: aircraft tied down, equipment moved to hangars, every non-essential movement stopped. She has seen typhoons track close to Kadena, but this time her base went to its highest readiness condition, the first time in 3 years the island had faced a storm this direct. She is watching the radar, doing every step of her job exactly right. What she cannot see from the flight line is that the storm she is preparing for is only the first half of what is coming. The JMAR's official advisory on June 2nd put the threat picture in plain operational language. I am reading from the text directly. The Meteorological Agency has warned of violent winds, high waves, storm surges, landslides, flooding and overflowing rivers in affected areas. Read that list one more time. Wind, waves, surge, landslides, flooding, rivers. 6 distinct hazard categories in one sentence. That is the maximum multi-hazard warning the agency issues. And the geographic scope of the warning was not limited to Okinawa, where the storm was hitting hardest. The advisory extended the warning level rainfall designations across the entire Pacific coast of Japan, from Kyushu to Kanto. Look at that geography on a map for a second. Kyushu is the southernmost main island of Japan. Kanto is the eastern region that contains Tokyo. The corridor between them runs more than 1,000 kilometers up the Pacific coastline, taking in Shikoku, the Kansai region, the Tokai region, and finally the Greater Tokyo Metropolitan area. The JMAR's warning covered every prefecture in that corridor. That is a single advisory covering a population of more than 80 million people. It is the kind of warning footprint you issue when you are not just worried about the storm at its current position. You are worried about what every part of that coastline is about to receive. Here is where the timing stops adding up. The advisory I just quoted from was issued on June 2nd. By June 2nd, Jangmi's central pressure had risen to 980 hectopascals. Wind speeds at the centre had dropped to 90 km per hour. The storm was accelerating northeast at 35 km per hour. Translation: in plain operational terms, the storm was weakening. The storm was moving away. By every standard meteorological rule of thumb, a typhoon that is weakening and accelerating delivers less total rainfall over any given point, not more. It does not have time to dump its moisture. It does not have the energy to sustain heavy precipitation. The integrated rainfall totals should be going down. The JAMA forecast the opposite. While the storm was weakening and accelerating, the agency issued a rainfall forecast of 200 to 300 millimeters for the Pacific Coast corridor, with the peak window arriving on June 3rd. That is the gap that does not close until you read the rest of the advisory. The JAMA was not forecasting Jangmi's rain. The JAMA was forecasting what the area was going to receive. Those are not the same thing. The agency knew it. The advisory text proved it. The Western media reports skipped the part of the text that explained why. Across Okinawa and Kagoshima prefectures, 48,000 homes lost power during the peak wind window. That number reflects the storm at its strongest. Power lines down, transformers blown, distribution networks knocked out by gust loads at the limit of what they were designed to handle. 16 people were confirmed injured in the prefectures hit hardest by the wind phase. Cuts from flying debris. Falls during evacuation. The injuries you expect when a typhoon passes close to a populated coastline. These are wind and surge consequence numbers. They reflect the storm at its strongest. But the warnings being issued at the same moment were not for the storm at its strongest. They were for what was coming next. The Kadena Air Base shutdown lasted through the peak window. Aircraft that had been moved to hangars stayed in hangars. The flight line stayed empty. Personnel sheltered in hardened facilities. Family housing across the base areas reported the kind of damage that comes from sustained 100-mile-per-hour gusts. Roof tiles displaced, windows blown out, trees stripped, cars dented by airborne debris. The base infrastructure took the storm and held. The American families on Kadena had insurance, evacuation plans, and the institutional muscle of the United States military behind them. They are not the most vulnerable population in this story. They are the population most able to recover. The most vulnerable population is not on Okinawa. The most vulnerable population is in the hills above the river valleys of western Honshu, the mountain prefectures of Shikoku, the drainage basins above Hiroshima and Okayama, the hillside neighborhoods of the Kansai cities, the river towns of the Tokai region, the exposed coastal flatlands of Kanto. These are the geographies the JMAR's June 2nd advisory was actually warning about. None of those geographies were in Jangmi's direct path. All of them were in the path of what Jangmi was about to feed. The JMAR issued maximum multi-hazard warnings at the exact moment the storm stopped being at maximum strength. That gap between what the storm was doing and what the agency was warning does not close until you find the sentence buried in the advisory text that nobody in Western media quoted directly. That sentence is the key. The JMAR advisory included a brief technical note explaining that rain would begin falling in affected areas even before the typhoon center arrived, driven by a stationary front positioned north of the storm. One sentence. Inside a longer technical document. Translated by no major English-language outlet that ran the story. The Western coverage focused on the typhoon's position, its wind speed, and the airport closures. The most important sentence in the advisory got dropped on the cutting room floor. This is not a criticism of the reporters who covered the storm. This is a structural problem in how international weather stories get translated for foreign audiences. The storm is the visual. The storm is the headline. The storm is what the satellite imagery shows. The front is invisible on most satellite imagery the average viewer sees. The front is not on the cone of uncertainty. The front does not have a name that fits in a headline, so the front gets dropped, and the warning that the JMAR was issuing about the front gets reduced to a generic flood warning attached to the typhoon. The 48,000 power outages reflect Jangmi. The 16 injuries reflect Jangmi. The 162 km/h gusts reflect Jangmi. Those are real numbers. They tell a real story. They are also not the story the JMAR was most worried about on June 2nd. The agency's most urgent warnings were for events that had not happened yet, in geographies the storm had not yet reached, driven by a system the storm was not directly responsible for. The agency was warning about the next thing. The Western coverage was reporting on the current thing. Those two stories diverged on June 2nd. They have not converged yet. By the time you finish this video, the JMAR's post-landfall impact assessment will be hours away from release. The numbers in that assessment will either confirm that the agency was right to issue the warning it issued, or they will reshape what we understand about how this combination of systems performs in real time. Either result tells us something important. The first tells us the warning system works. The second tells us where the gap between forecast and reality lives in the data. For the next several minutes, we're going to follow the evidence the JMAR was actually responding to. The rain that started before the typhoon arrived. The system that was already positioned over Japan when Jangmi was still hundreds of kilometers south. The mechanism that connects a weakening storm to a catastrophic rainfall forecast in a way that violates every standard rule about how typhoons deliver their water. The rain that was about to fall on western Japan was not going to come from Jangmi's center. It was going to come from something that had been sitting over Japan for weeks, something the typhoon was feeding from hundreds of kilometers away, and by the time most people realized it, the rain would already be falling. Part 2. What already started. By midday on June 2nd, residents in Kyushu were reporting steady rainfall. Jangmi was still hundreds of kilometers to the south. The storm had not yet approached the main islands. The rain was not from the typhoon. It was already there, falling from a system positioned over Japan that had been in place for days, and what was about to happen to that system as Jangmi closed in from the south was the specific thing the Japan Meteorological Agency tried to describe in their advisory, and that no Western headline translated. The advisory stated plainly, rain may fall in some areas even before the typhoon hits, due to a stationary front north of the system. That sentence is the most important piece of operational language in the entire document. It tells you that the agency knew the rain was not going to come from the typhoon. It tells you that the agency was forecasting accumulation from a separate system. It tells you that the agency was issuing the warning based on cumulative impact, not point impact. And it tells you that the standard reading of the warning, the one that treats it as a typhoon flood warning, misses the point of what the agency was actually trying to communicate. The JMA's specific rainfall forecast by noon on June 3rd was structured around region. 300 mm for Shikoku and the Kansai region. The Kansai region includes Osaka, Kyoto, and Kobe. The combined population of that region is approximately 20 million people. 200 mm for the Tokyo region and Kanto. The Kanto region includes Tokyo. The population of Greater Tokyo is approximately 37 million people. Average monthly rainfall for Tokyo in June is approximately 160 mm. The forecast was for more than a full month of rain in under 24 hours. Let that translation sit for a moment. A month of rain in less than a day. In a city of 37 million people. Tokyo's drainage system is among the best engineered in the world. The Kasukabe Underground Flood Control Facility, sometimes called the Underground Temple, can divert massive volumes of stormwater from the rivers above the city. The engineering is real. The engineering also has limits. When the rainfall rate exceeds the system's intake capacity for sustained periods, the system stops being a buffer and starts being a backlog. Surface water accumulates. Lower elevation neighborhoods take on water. The system holds for hours longer than the rainfall would otherwise predict. Then it does not hold. The Kasukabe facility is worth understanding in concrete terms because it is the single most impressive flood engineering project in the world. And the fact that the JMARS forecast makes it relevant right now tells you something important about the scale of what the front is expected to deliver. The facility sits 50 meters underground, beneath the northern suburbs of Tokyo. It connects 5 separate river systems that run north of the city to a massive underground cistern through a series of tunnels, each large enough to drive a truck through. When the rivers rise above their bank thresholds, automatic gates divert the overflow into the tunnels. The water travels underground, fills the cistern, and is pumped out into the Edo River at the facility's southern end. The system can move 200 cubic meters of water per second. It took 13 years to build and cost the equivalent of $3 billion. Japan built it because Tokyo floods. The city sits on a flat alluvial plain, crisscrossed by rivers that carry runoff from the mountains to the north and west. Before the Kasukabe facility existed, any heavy rainfall event that overwhelmed the urban drainage system sent water into the streets. After the facility opened, the frequency of major flooding in the northern Tokyo suburbs dropped significantly. The engineering worked. And there is a number above which even the Kasukabe facility stops being a solution. 200 millimeters of rainfall over the greater Tokyo area in under 24 hours, falling on ground already saturated from 3 weeks of front rainfall, pushes the river systems faster than any underground diversion system can handle. The facility was designed against the historical rainfall record. The historical rainfall record, as of the last decade, is not the record anymore. The front has entered a new climate state. The infrastructure was not updated to match. That is not a criticism of Japanese engineering. Japanese flood engineering is the best in the world. It is a statement about the gap between what the infrastructure was designed for and what the mechanism now produces when the design envelope and the event envelope no longer overlap. Engineering that was adequate becomes inadequate, not because the engineering failed, but because the event changed. That is the position Tokyo's flood infrastructure is in on the night of June 2nd, 2026. The drainage systems will work. They will work right up to the point where they cannot, and what happens after that point is what the JMARS warning is actually describing. The same arithmetic applies to every other major city in the Pacific Corridor. Osaka has its own drainage infrastructure. So does Kobe. So does Nagoya. None of them are designed to handle a month of rain compressed into a single day on top of 3 weeks of pre-existing saturation. The engineering tolerance assumes the ground around the city has some residual capacity to absorb water that the urban systems cannot move fast enough. When the ground has no residual capacity, the equation breaks down at every level simultaneously. Japan experiences the Baiu season every year from approximately late May through mid-July. The word Baiu translates roughly to plum rains. It is the East Asian monsoon's rainy period, the seasonal phenomenon that delivers the bulk of the country's summer water supply. The front delivers weeks of persistent moderate rainfall. Farmers rely on it, rivers fill from it, soil saturates during it. By the first week of June, any ground in western or central Japan has already absorbed weeks of Baiu rainfall. It is not the first rain on dry ground. It is more rain on already saturated ground. That distinction is what turns a rainfall forecast into a landslide forecast. The physics of slope failure is not complicated. Soil holds water up to a specific capacity. Below that capacity, water adds weight, but the hillside holds. Above it, the soil becomes mechanically unstable and the slope fails. The hill comes down. That failure threshold arrives much earlier in a rainfall event, when the soil starts out already partially wet, which is exactly the condition across western Japan in early June after weeks of seasonal front rainfall. Picture a rice farmer in the Kumamoto flatlands checking his drainage channels on the morning of June 2nd. His fields have already taken 3 weeks of Baiu rainfall. The channels are moving water but not overwhelmed. He has farmed this land for decades. He knows the plum rains. He knows what normal looks like. What he does not know on June 2nd is that the drainage system he trusts, built for the normal Baiu season, is about to receive 5 or 6 days' worth of additional rainfall in the next 18 hours. He is making decisions based on 30 years of experience with what June rain looks like. Those 30 years do not include what happens when the seasonal front gets loaded from the south by a typhoon. By the afternoon of June 2nd, he has decided his drainage channels can handle whatever arrives. He has decided not to move his equipment to higher ground. That decision is based on everything he knows. What he does not know is that the rainfall about to arrive will exceed the capacity of his drainage channels in the first 3 hours, and by the time he realizes the water is not moving the way it should, the only road out of his section of the flatlands will already be underwater. The JMAR's warning level designation for rainfall covers the probability of dangerous accumulation relative to the ground's current capacity to absorb it. That is the operational definition. Read it carefully. The warning is not about the rainfall amount in isolation, it is about the rainfall amount relative to the ground's capacity. 200 millimeters of rain on dry ground in October is a different warning than 200 millimeters of rain on saturated ground in early June. The agency knows the difference. The classification reflects the difference. The Western coverage almost never reflects the difference. Saturated ground in mountainous terrain like Japan's means the critical threshold for landslide risk arrives much earlier in a rainfall event than it would for dry ground. The hillsides above the Hiroshima suburbs, the slopes above the towns of Ehime Prefecture on Shikoku, the river catchment areas above the Kansai cities, the mountain communities of the Kii Peninsula. Every one of those geographies starts the June 3rd rainfall event with soil already at or near the threshold where a few more hours of intense rain triggers slope failure. The JMAR knows this. The classification is built around it. The warning was issued because the agency's models showed exactly this combination of starting condition and incoming rainfall. The JMA's warning level issuance for the full Pacific Coast Corridor was not based on a single rainfall event in isolation. It was based on cumulative soil saturation plus incoming additional rainfall. The typhoon was accelerating and weakening. The ground was already full. Those two facts taken together explain the entire warning. The storm did not need to deliver a catastrophic amount of rain to produce a catastrophic outcome. It only needed to add enough additional water to a system that was already at its limit to push it past the failure point. The ground under western Japan on June 2nd was not waiting for a typhoon. It was already past the point where one more day of normal Baiu rain would have been enough to trigger slides. The JMAR runs a nationwide network of automated rain gauges, river level sensors, and soil moisture monitoring stations across every prefecture in the forecast zone. What those sensors showed on the morning of June 2nd was not a dry country waiting for rain. It was a country already at the upper boundary of what normal absorption looks like. Japan river management authorities classify river levels on a 5-step scale. Level 1 is low water. Level 3 triggers flood advisories. Level 5 requires immediate evacuation orders for riverside communities. On the morning of June 2nd, multiple river systems in the warning zone were running at level 2 to 3. Not because the typhoon had arrived, because 3 weeks of Baiu season rainfall had been filling them from above while saturated ground fed them from below. That starting level matters more than most viewers understand. A river at level 2 behaves completely differently from a river at level 1 when heavy rainfall begins. The time between the start of heavy rain and the moment the river exceeds its flood bank compresses dramatically. Under dry conditions, a river starting at level 1 might absorb 8 to 12 hours of sustained heavy rainfall before presenting a real flood risk. A river starting at level 2 might reach the same danger threshold in 3 to 4 hours. The margin the population has to receive warnings, make decisions, and reach safety shrinks by more than half. That compression does not appear in any headline. It sits inside the river-level data the JMAR was examining when the agency issued the warning covering 80 million people. Japan also runs a sediment disaster warning system, a joint program between the national government and the prefectural authorities that monitors slope stability across 680,000 designated landslide hazard zones nationwide. Before the amplified rainfall from this event arrived, that system was already flagging elevated risk across much of Shikoku, the Kii Peninsula, and the mountains above Hiroshima and Okinawa. The Soil Water Index, the metric the system uses to measure how much water the soil column is holding, was running at approximately 150 to 200% of the seasonal baseline for early June across the most vulnerable mountain zones. The soil held twice as much water as it normally does at this point in the calendar year. There was no slack left in the system. Any additional significant rainfall would go directly to slopes already at or near the mechanical failure threshold. What was coming was not one more day of normal. It was the front amplified. That amplification is the specific mechanism we have not yet named, and it is the entire reason the JAMA's warning was structured the way it was. The agency knew the front was already loaded. The agency knew the typhoon was approaching. The agency knew the historical precedent. The advisory contained the operational language. What the advisory did not contain, because no operational forecast document does, was the narrative explanation that connects the technical language to the historical event that proves what this combination produces. That explanation is the gap. The gap is what this video is filling. The JAMA said what it knew. The advisory contained the relevant language. The word front appeared in the official text. What the agency did not do, and is not institutionally structured to do, is provide the narrative bridge between a technical meteorological advisory and the 2018 historical precedent that shows exactly what happens when this combination of saturated ground, stalled front, and incoming typhoon moisture arrives at the same place at the same time. That bridge is the gap. The data is in the JAMA's own text. The implication is not. Translating an operational forecast into a public threat narrative is not the JAMA's job. The agency forecasts. It does not interpret historical precedent in real time for a public audience. That interpretation belongs to media. That interpretation, for international audiences watching from outside Japan, belongs to the Western outlets that picked up the typhoon story. Those outlets did not connect the dots. The technical language in the advisory was there to be quoted. The 2018 parallel was there to be drawn. The narrative bridge was not built. So the warning landed in international coverage as a generic typhoon flood warning, and the most important part of what the agency was actually communicating did not make it through translation. The cost of that translation failure is measured in evacuation decisions. People who watched coverage of a weakening typhoon and concluded their area was safe. People who saw a track map that showed the storm moving away and decided to stay in place. People who heard rainfall totals attributed to the typhoon and assumed those totals would taper as the storm weakened. Every one of those decisions was made with incomplete information. Not because the JAMA failed, because the chain from JAMA to international viewer dropped the sentence that mattered most. There is a specific name for what happens when a typhoon's warm, wet circulation collides with a stalled Baiu front and locks it in place. That name has been in the scientific literature for years, documented by researchers at 2 Japanese universities with satellite data going back more than 2 decades, and it explains every number you have heard in this video so far, in a way that no single weather forecast was saying out loud. Part 3. What nobody connected. Japan has a weather system that arrives every single June without fail. It has a name in Japanese, Baiu, meaning plum rains. It sits over the country as a stalled front, a boundary between warm tropical air from the south and cooler continental air from the north, and it delivers weeks of persistent rainfall before the summer heat drives it away. Every farmer in Japan knows it, every forecaster in Japan tracks it, and every year, for a few critical weeks, this seasonal front is the most important weather system over the most densely populated arc of land in East Asia. In most years, it is manageable. In the years when a typhoon approaches from the south while the front is still in place, the rules change. Let me show you what this seasonal front actually is in operational terms. It is a quasi-stationary east-Taoist weather boundary, meaning a boundary that essentially stops moving and holds position, forming over Japan and the surrounding Pacific every June and July. Hours pass. Days pass. The boundary holds its position. It does not march across the map the way a cold front does. It sits. The warm, moist air from the Pacific pushes against the cooler, drier air from the Asian continent, and the boundary between them becomes the delivery point for persistent rainfall over the same geography for weeks at a time. Japan's mountainous terrain amplifies this delivery in a way that flat geographies do not experience. Rain that falls on steep slopes does not slowly soak in across a wide, flat catchment. It accelerates downhill, channels into streams, fills tributaries within hours, and reaches main rivers far faster than equivalent rainfall would on flat terrain. Rivers that are already running high from weeks of Baiu rainfall have no additional capacity when the next rain event arrives. The water has to go somewhere. It goes into the floodplain. It overtops the banks. It enters communities that were not in any standard flood map at the start of the season. On June 2nd, 2026, the seasonal stalled front was confirmed active and stationary north of Jangmi's track. The JMARS advisory explicitly noted its presence as the source of pre-arrival rainfall. The front was not weakening. It was not moving. It was sitting in exactly the position that, historically, produces the most catastrophic outcomes, above already saturated terrain, below a typhoon's advancing moisture field, locked in place by the interaction between the two systems. That position is not random. It is the same position this front occupied in early July 2018, in the days before the worst freshwater flood disaster Japan had experienced in nearly 4 decades. Here is what the combination does in plain physical terms. A typhoon's outer bands extend hundreds of kilometers from the center. They carry warm, wet air at near saturation moisture levels, the richest moisture load the atmosphere produces. As the storm moves north, those outer bands push that moisture into the stalled seasonal front ahead of them. The front was already delivering moderate rainfall. Now it receives a massive additional moisture injection. Rainfall rates jump, not by a few percent, by multiples. What had been delivering 5 mm per hour can reach 30, 40, 50 mm per hour over the same geography. The hourly rate matters more than the total, because hourly rate is what determines whether drainage systems can keep up and whether soil can absorb water without failing. The front cannot move north to escape the input because the cooler continental air to its north holds it in place. The pressure pattern that keeps the front stationary in normal Baiu conditions becomes a trap when the moisture injection arrives. The front would, under different conditions, move north toward the cooler air and dissipate as it crossed the temperature gradient. But the continental high pressure to the north of Japan in early June is a stable feature. It does not yield. The front is held against it from below by the typhoon's circulation. It cannot escape upward. It cannot escape sideways. It can only release the moisture in place. Picture a woman living in a hillside neighborhood in the Hiroshima suburbs, watching the forecast on June 2nd. The news is showing a typhoon track. The typhoon is weakening. She has seen typhoons come close before and produce less damage than forecast. She has no reason to believe this one is different. What the television is not showing her is that the heavy rain forecast for her area on June 3rd will not come from the typhoon's centre at all. It will come from the front sitting directly above her neighbourhood, loaded with moisture that is being pushed northward by the typhoon from 400 kilometres away. Her evacuation decision on the night of June 2nd will be based on information about a weakening storm, not information about what is actually positioned over her house. The storm was never the threat. The front cannot dissipate because the typhoon keeps feeding it from the south. As long as the typhoon's outer circulation remains in range, the moisture pump stays on. That is the critical insight. The storm does not have to be close. The storm does not have to be strong. The storm only has to be near enough that its outer bands continue to push tropical moisture northward into the front. Jangmi at 980 hectopascals, weakening, accelerating northeast, is still close enough and still carrying enough moisture in its outer circulation to keep the pump running for the duration of the relevant window. The storm locks the front. The front delivers the rainfall. And then the front delivers. The same geography receives heavy rainfall not for hours, but for days, long after the typhoon has passed and weakened into nothing. This is the part that breaks every standard intuition about how typhoons cause damage. The typical model says, storm approaches, storm hits, storm passes, damage is done. The damage is concentrated in the window of the storm's presence. In a Typhoon Baiu front interaction event, the damage window extends well beyond the storm's presence, because the front continues delivering rainfall after the storm is gone. The trigger leaves, the mechanism continues. That gap between when the typhoon clears and when the rain finally stops is where the death tolls climb. The combination of a saturated surface, a locked front, and continuous moisture injection from an approaching typhoon is more dangerous than any single element alone. Each element by itself produces a manageable outcome. A typhoon with maximum winds but no stalled front produces concentrated damage at the point of landfall. The wind does its damage. The surge does its damage. The rain falls in a relatively narrow window as the storm passes through, and then the storm moves on. Cleanup begins. Lives are lost in the landfall window, but the event has a clear beginning and end. A stalled front without a typhoon produces persistent moderate rain, but rarely catastrophic accumulation. The Baiu season in a typical year delivers weeks of useful rainfall. Rivers fill. Reservoirs refill. Agriculture benefits. Some flooding occurs in low-lying areas during particularly intense Baiu rainfall events, but the rates rarely reach the threshold where slopes fail or drainage systems break down. The front holds. The country absorbs the water. Life continues. The two systems together produce what the data from 2018 documented in numbers. 1,243 mudslides in a single prefecture. 225 deaths. Nearly $10 billion in damage, from a storm that was already weakening when the worst of it began. Those numbers are not a worst-case projection. They are the recorded historical result of a Typhoon Baiu front interaction event running at full strength over saturated ground in the early Baiu season. The 2018 event is the proof of what this mechanism does. It is the floor on the worst-case scenario, not the ceiling. Every rainfall total you have heard attributed to Jangmi in this video was not produced by Jangmi. It was produced by the system Jangmi was feeding. And that system has a name that finally makes the whole picture clear. Before we get to that name, I want you to understand one more thing about why this specific configuration is so hard to communicate to a general audience. There is nothing on a standard weather map that shows what is about to happen. The typhoon track is visible. The cone of uncertainty is visible. The wind speed and pressure readings are visible. The front is sometimes shown as a line on specialist forecast products. But the interaction between the two systems, the specific process by which a weakening typhoon loads a stalled front from hundreds of kilometers away, produces no visible signature that a viewer watching standard weather coverage would recognize as dangerous. A strong typhoon making direct landfall looks alarming on every instrument. The satellite image shows a tight circular eye. The pressure trace shows a sharp drop. The wind speed spikes at each sensor as the eyewall passes. The storm surge gauge rises. The event has a clear visual signature that the public and the media can track in real time and watch arrive. A Typhoon Baiu front interaction event has none of that visible drama until it is too late to use the information. The front is a diffuse zone on the satellite image that has been there for weeks. The typhoon is weakening, so every storm intensity instrument is moving in the wrong direction for alarm. The rainfall gauge in a mountain valley starts climbing, but it has been climbing modestly for 3 weeks, and the new readings look like a continuation of normal. The river sensor rises, but it has been rising slowly for days. Nothing triggers the automatic pattern recognition that signals danger until the slope fails and the road disappears. This is the technical gap that makes Typhoon Baiu front interaction events consistently more deadly than their typhoonally counterparts in the historical record. Every instrument tells the story of a storm that is finishing. The mechanism producing the casualties is invisible at the instrument level until the threshold is crossed. The only early warning is the forecaster watching both systems as a combined event. The JMAR was that forecaster on June 2nd. Almost no one else was. What science cannot yet fully predict is the precise timing and location of the rainfall maximum when a typhoon and a stalled Baiu front interact. The JMAR can forecast a range 200 to 300 millimeters. Shikoku and Kanto. By noon June 3rd, but the specific valley where a river crests first, the specific hillside where the soil gives way first, the specific hour when the drainage system fails, those remain outside the model's resolution. The warning is accurate. The precision is not available. That gap between accurate warning and precise prediction is where the casualties happen. The precision gap exists because rainfall maxima within a stalled front depend on small-scale atmospheric variations that current forecast models cannot resolve. Those variations include local temperature gradients across valley openings, the exact position of low-level jet streams feeding moisture into the front, and the orographic forcing effects of specific ridgelines that channel airflow in ways that concentrate rainfall on one slope rather than the adjacent one. These factors operate at spatial scales of 1 to 10 kilometers. The standard forecast models used by the JMAR and every other major forecasting agency run at spatial scales of 5 to 20 kilometers. The models can tell you the front is loaded. They can tell you the broad region where the heaviest rain is likely. They cannot tell you which specific valley receives the burst that triggers the slide, or which specific hour that burst arrives. That gap between broad warning and precise prediction is where the casualties happen. Not because the warning is wrong, the warning is right. The 200 to 300 millimeter forecast for the June 3rd window is accurate at the regional scale. What it cannot tell any individual household is whether their specific hillside or their specific drainage system sits inside the highest intensity cell or sits 5 kilometers away in a zone receiving half as much rain. Those 5 kilometers can be the difference between a flooded basement and a collapsed hillside. The warning system is operating at the limit of what current atmospheric science can deliver. The limit is not a failure of the agency, it is the current boundary of the science. Understanding where that boundary sits is what allows you to use the warning correctly. That is why evacuation orders in events like this are necessarily broad. Local authorities cannot pinpoint which neighbourhoods will see the worst rainfall in advance. They have to issue warnings for entire regions and trust residents to take precautions based on local risk knowledge. Residents who live below known landslide zones evacuate earlier. Residents in lower elevation flood-prone areas move to higher ground. Residents who do not know their property is in a high-risk position make decisions based on the broad forecast without the geographic precision that would tell them whether their specific location is in the most dangerous part of the warning zone. The mechanism connecting the weakening typhoon to the catastrophic rainfall forecast has been documented by Japanese researchers using 23 years of satellite data, confirmed in a peer-reviewed study, and referenced in the JMAR's own advisory language. In Part 4, we are going to name it exactly, explain what it does step by step, and show you why every news report you have seen about this storm has been tracking the wrong system. Part 4. What it is actually called. Everything in Parts 1, 2 and 3 points to the same thing. The weakening storm issuing maximum warnings, the rain that started before the typhoon arrived, the stalled front sitting over already saturated ground, the 200 to 300 millimeter forecast for a city of 37 million people. None of those data points are isolated facts. They are the outputs of one specific process. And the mechanism driving all of this has a name. It has been in the scientific literature for years. Almost no one outside the forecasting community is saying it. We are going to say it now. The mechanism driving this is called Typhoon Baiu front interaction. When a typhoon's outer circulation pushes warm, wet air northward into a stalled Baiu front sitting over Japan, the front locks in place and amplifies its own rainfall output far beyond what it would produce without the typhoon's moisture. The typhoon does not have to make landfall to cause catastrophic rainfall. It only has to approach. This is why the storm was weakening while the warnings were intensifying in Part 1. This is why rain was falling over western Japan before the typhoon arrived in Part 2. This is why the stalled front in Part 3 was the actual delivery system and not the storm itself. The typhoon was the fuel source, the Baiu front was the engine. They are two separate systems producing one combined output that is more dangerous than either could produce alone. On June 2nd, 2026, the JMAR confirmed both systems were active and in the precise configuration this mechanism requires. The Baiu front was stationary over Japan. Jangmi's moisture field was feeding it from the south. The rainfall had already begun in Kyushu. The main delivery event arrived on June 3rd. Now you know what you are looking at. Everything before this moment was the setup. This is the answer. Every number we have walked through, every advisory line we have quoted, every gap in the Western coverage we have identified, traces back to this single-named mechanism. The agencies tracking Japan's weather know it. The researchers who study Pacific tropical systems publish on it. The forecasters at the JMAR write advisory language around it. The viewer at home, watching a weakening typhoon on the news, almost never hears its name. The data from Tokyo Metropolitan University and Nagoya University covers 23 years of satellite radar observations documenting the enhancement of heavy rainfall along the seasonal stalled front in East Asia. The word Meiyu is the Chinese equivalent of the Japanese Baiu. The two terms describe the same continental front system as it crosses the East Asian rainy belt. The Chinese segment is called Meiyu. The Japanese segment is called Baiu. The mechanics are continuous across the region. The research team analysed satellite measurements of precipitation along this front, going back to 1998, and compared the recent decade to the decade before it. The satellite record shows heavy precipitation frequency along this front increased 24% between 1998 to 2008 and 2009 to 2019. Let that translation sit. Heavy precipitation events along this specific front, the same front that produces the events we are talking about, became almost a quarter more frequent in the most recent measured decade compared to the prior decade. The front is not static. It is becoming more intense decade over decade. The mechanism they documented is the same mechanism active over Japan right now. The baseline is moving. The current configuration is operating above the historical reference point that earlier studies were calibrated against. The published analysis describes this front as having entered a new climate state requiring revised disaster prevention approaches. That phrase, new climate state, is not rhetorical. It is scientific language describing a measured, confirmed shift in the behavior of a weather system that 100 million people in Japan depend on for seasonal rainfall. When researchers use the phrase new climate state, they are saying the historical baseline no longer applies. The frequency, the intensity, and the consequence range of biorelated extreme rainfall events are operating in a regime that differs measurably from the regime that produced the historical disaster prevention infrastructure currently in place. The researchers who documented the 24% increase in heavy rainfall along this front did not describe it as a trend still developing. They described it as a new state already arrived. That means the baseline year for comparison is not the 1990s or the 2000s. It is 2018. And 2018 is the floor, not the ceiling. On June 2nd, 2026, the JMAR's advisory text confirmed both the Baiu front's activity and Jangmi's role in feeding it. The advisory stated that rainfall would begin before the typhoon arrived. It specified the front's location as the source, that is, Typhoon Baiu front interaction described in operational language by the primary forecasting agency for the country most affected by it. The mechanism was named indirectly. No Western outlet named it directly. The agency does not need to use the scientific term in a public advisory. The agency uses operational language designed for emergency managers, prefecture officials, and trained meteorologists. The implicit naming is enough for the audience that consumes the advisory in its original form. The translation problem is a different audience problem. International viewers consuming the story through English-language Western outlets do not get the implicit naming. They get the explicit headline. The headline is the typhoon's name, the typhoon's wind speed, and the typhoon's track. The implicit naming of the mechanism, embedded in the agency's operational language, does not make it across the translation gap. The international story becomes a generic typhoon story. The specific mechanism that distinguishes this typhoon from a normal Pacific storm of comparable strength stays inside the Japanese language source material. That gap is not a failure of any individual outlet. It is a structural feature of how international weather news gets packaged for foreign audiences. The headlines have to fit a frame the audience already understands. Typhoon, wind, rain, track forecast. Anything that requires explaining a mechanism that is not already in the audience's vocabulary gets cut for word count or buried in a paragraph below the fold. The Baiu front, the stationary front mechanism, the moisture injection dynamics, the soil saturation interaction with slope failure thresholds, all get compressed or dropped in favour of the headline-friendly storm details. What Typhoon Baiu front interaction means for the near-term forecast is this. The rainfall totals on June 3rd will not track with Jangmi's position or intensity. They will track with the front's behaviour. A forecaster watching only the typhoon's position and wind speed will see a weakening storm moving fast and predict decreasing rainfall. A forecaster watching the Baiu front will see a locked system receiving continuous moisture injection and predict sustained, potentially catastrophic accumulation. Those two forecasts describe the same event in completely different terms. Only one of them matches 2018. The JMARS forecast matches the second view. The agency is not predicting decreasing rainfall. The agency is predicting sustained heavy rainfall through the noon June 3rd window across the entire Pacific corridor. That forecast is operationally inconsistent with the typhoon-only model. It is operationally consistent with the Typhoon Baiu front interaction model. The agency's forecast is, in effect, an implicit declaration that the mechanism is active and that the standard typhoon-only rules do not apply to this event. The historical record on Typhoon Baiu front interaction events tracks back further than the 23-year satellite dataset. Japan has experienced devastating flood events from this same combination multiple times in the post-war era, and the pattern is consistent across every decade. Start with 1959. The Ise-1 typhoon, also called Typhoon Vera, made landfall near Nagoya in September of that year. 5,118 people died. It remains the deadliest single weather event in Japan's post-war history. The typhoon itself was powerful, a direct landfalling storm with extreme winds and surge, but the death toll in the interior prefectures, away from the coast where the surge hit, was driven by rainfall. The typhoon's circulation interacted with a stationary frontal system already positioned over central Honshu. The front locked. The rivers of the Nobi Plain, a flat agricultural region north of Nagoya, received rainfall at rates the system had never been engineered to handle. The plain flooded. Communities that had been built on reclaimed coastal land, below sea level, had no means of drainage once the levees overtopped. Families survived on rooftops for days. The event reshaped Japan's entire approach to flood engineering, producing the national disaster prevention infrastructure that still exists today. The 1959 death toll was the proof of concept that drove half a century of Japanese flood control investment. Move forward to 1982. The Nagasaki floods in July of that year produced 299 deaths in a single prefecture over a 48-hour window. The event was not driven by a direct typhoon landfall. A weakened tropical system approaching from the south fed moisture into a stationary front positioned over Kyushu. Sound familiar? The rainfall totals in the worst affected areas of Nagasaki Prefecture reached 572 millimeters in 24 hours in some catchment areas. The hillsides above the city of Nagasaki gave way in hundreds of locations simultaneously. The event was Japan's deadliest freshwater disaster between 1959 and 2018, until 2018 broke that record. And 1998. Northern Japan. A stationary front over Tohoku received moisture injection from a tropical system tracking through the East China Sea. The flood event killed 28 people and displaced tens of thousands. The numbers are smaller than 1959 or 1982, but the mechanism is identical. The front was in position. The tropical moisture arrived from the south. The front amplified. The rainfall exceeded every drainage threshold in the affected catchment areas. The pattern repeats because the geography has not changed and the mechanism has not changed. What has changed, as the satellite data confirms, is the frequency. The interval between events at the upper end of the severity range is shortening. What the post-war record shows, taken as a whole, is that Japan has been experiencing this mechanism for as long as the country has had modern meteorological records. The disasters are not random extreme weather events. They are predictable outputs of a predictable mechanism operating on predictable seasonal infrastructure. The 1959 event should have been enough. The 1982 event confirmed it. The 1998 event reinforced it. The 2018 event, the deadliest in 36 years, proved that the mechanism is not becoming less dangerous as infrastructure improves. It is becoming more frequent as the front intensifies. The science that confirmed that intensification was published in 2021. The event it most directly predicts is happening right now. What the post-war record shows is that the mechanism is not new. The mechanism has been delivering catastrophic events to Japan for as long as the country has had modern meteorological records. What is new is the documented increase in frequency. The 24% jump in heavy precipitation frequency along the front in the recent decade is a measured change in the baseline. The events are still rare in absolute terms. They are becoming less rare. The interval between events at the upper end of the historical severity range is shortening. Picture a retired schoolteacher in Kochi City on Shikoku Island, whose house sits on a hillside above the Kagami River. On the night of June 2nd, she has watched the news about the typhoon. She has seen that it is weakening. She has decided not to evacuate because the storm appears to be losing strength. What she did not hear in any news report she watched was that the 300mm rainfall forecast for her region by noon June 3rd is not the typhoon's rain. It is the Baiu front's rain, already positioned directly above her house, being loaded from below by Jangmi's moisture field. Her decision to stay was rational given the information she received. It was made without the one piece of information that would have changed it. What Typhoon Baiu front interaction does not yet tell us is the exact threshold at which the interaction becomes catastrophic versus damaging. The 2018 event produced 225 deaths. Other years with similar configurations produced significant flooding, but far fewer casualties. The difference between those outcomes involves factors that the current models handle imprecisely: the exact saturation level of the soil at the time of maximum rainfall, the precise position of the front relative to specific river catchment areas, the window of time between when residents receive warnings and when the conditions become impassable. The mechanism is confirmed, the exact outcome is not. Honest uncertainty is the only intellectually defensible position here. The science documents that Typhoon Baiu front interaction produces greater rainfall than either system alone. What the science cannot yet quantify precisely is the exact multiplier in any specific event. The 2018 total was catastrophic. The 2026 total may be less, it may be comparable. The mechanism is the same. The outcome range remains wide. That uncertainty is not a reason to discount the warning. It is the reason the JMAR issued the warning it did. A wide outcome range, in operational terms, means the agency cannot predict the specific event, but must prepare for the upper end of the plausible distribution. That is what the warning is doing. It is not predicting that this event will be 2018. It is acknowledging that the conditions are present for an outcome within the same range as 2018, and warning the population accordingly. The agency is doing exactly what a responsible forecasting agency does when the mechanism is confirmed active and the outcome distribution is wide. It issues the warning at a level that protects the population from the upper end of the distribution, accepting the cost of false alarms in low-end outcomes to avoid the cost of missed warnings in high-end outcomes. This is why the warning is not hyperbolic. The warning is calibrated. It reflects exactly the uncertainty that the science cannot yet resolve. The agency is not overstating the threat. The agency is communicating the threat at the level that the mechanism and historical record support. Anyone reading the advisory and concluding the warning is excessive is reading it without the historical context that the agency is operating with. Anyone reading the advisory and concluding the warning is just routine flood language is missing the specific operational distinction the agency drew when it included the front-related language in the advisory text. The 2018 floods are the most powerful proof that this mechanism produces exactly the consequence the JMAR is warning about right now. In Part 5, we're going to go through what happened in 2018 step by step, because the numbers from that event are the only honest answer to the question of what Typhoon Baiu front interaction actually does to a country when it runs at full strength. Part 5. What 2018 proved. In late June and early July of 2018, Japan experienced what the Japan Meteorological Agency officially designated its worst freshwater disaster since 1982. It was not caused by the strongest typhoon of the year. It was not caused by a direct hit on a major city. It was caused by the same interaction we have just named, playing out over the same geography now in Jangmi's path, triggered by a storm that was already weakening as the worst of the damage began. The numbers from that event are the most honest translation of what the current forecast means. Let me pull up the official numbers from the JMAR's post-event analysis. The 2018 Japan floods killed 225 people across 15 prefectures. 225 people, spread across 15 separate prefectures, which means the event was not a single concentrated disaster, but a regional catastrophe affecting a corridor of the country roughly equivalent in scale to the eastern United States seaboard from Virginia to Massachusetts. 2 million people were displaced from their homes by flooding, evacuation orders, or destroyed infrastructure. Property damage reached $9.86 billion. That figure includes residential damage, commercial damage, agricultural losses, and the infrastructure rebuilding cost in the affected prefectures. In Hiroshima Prefecture alone, 1,243 mudslides were recorded. That number, 1,243, is not a regional total. It is a single prefecture total. Hiroshima Prefecture covers approximately 8,400 square kilometers. More than 1,200 hillsides in that one area gave way. The mudslides ranged from small slope failures that buried roads to large debris flows that destroyed entire hillside neighborhoods. Rescuers could not reach many of the affected communities for days because the roads themselves had disappeared under mud. Helicopters became the only access method for some villagers. Residents trapped by slides above and below their positions waited for evacuation while the rainfall continued. Picture a rescue worker in Hiroshima Prefecture, deployed in the days following the 2018 floods. Her team has been trying to reach a neighborhood cut off by 3 separate landslides on converging roads. She has the address of a family that had not evacuated. She has GPS coordinates. She does not have a passable route. The mudslides that blocked every access road to that neighborhood did not come from the typhoon. They came from days of rainfall delivered by the Baiu front after the typhoon had already passed. The storm was gone. The killing was not. The front kept delivering rain onto ground that had no more capacity to hold it, and the hills gave way one after another in the hours that mattered most. The trigger for the 2018 disaster was Typhoon Praporun. It was a Category 1 typhoon. It was weaker than Jangmi at peak intensity. It had already begun to lose strength as it moved through the region. Praporun never made a direct catastrophic landfall on a major city. The typhoon's track took it through the East China Sea, brushing the southern edges of the Japanese archipelago and then moving away to the northeast. By every standard metric that the international weather press would use to evaluate a typhoon, Praporun was a minor event. The headlines treated it that way. The headlines were wrong. The Japan Meteorological Agency's post-event analysis documented exactly what happened. The extreme rainfall was not caused by the typhoon's direct winds or surge. It was caused by the typhoon's warm, moist outflow feeding into the stalled Baiu front positioned over western Japan. The front locked. The moisture accumulated. The rain that fell on Hiroshima, Okinawa, Ehime, and 11 other prefectures was the Baiu front's output, amplified by Praporun circulation from hundreds of kilometers away. That is the mechanism. It is the same mechanism confirmed active right now. Let me make the comparison between 2018 and 2026 as direct as possible, because the parallel is not approximate. It is specific in every parameter that matters. In 2018, the Baiu front was in position over western Japan in the first week of July, approximately 2 weeks later in the season than the current event. The front had been delivering above normal rainfall since late June. Soil moisture across Hiroshima, Okinawa, and Ehime prefectures was running at elevated levels relative to the seasonal average. The rivers above those cities were running high. The drainage reservoirs were carrying more water than they typically hold in early July. That is the starting condition. In 2026, the Baiu front has been in position over western and central Japan since late May. It is now in the first week of June, approximately 2 weeks earlier in the season. Soil moisture is running at elevated levels relative to the seasonal average for early June. The rivers in the forecast zone are running above their early June baseline. The same starting condition exists, displaced by 2 weeks on the calendar and shifted slightly north in geography to include the Kanto region in the primary forecast zone, rather than concentrating the risk on western Japan alone. In 2018, Typhoon Praporun reached its peak intensity at around 965 hectopascals. It began weakening before its outer circulation reached the front. The outer circulation was still large enough and still moistureric enough to inject a sustained pulse of tropical moisture into the waiting front. The front responded. Rainfall rates in the affected catchment areas jumped from background Baiu levels to extreme accumulation rates within hours. The jump happened before Praporun had passed. It continued after the typhoon moved away. In 2026, Typhoon Jangmi reached its peak at 975 hectopascals. Slightly weaker at peak than Praporun was. By June 2nd, as Jangmi moved northeast, its outer circulation was still delivering a moisture pulse northward into the stalled front. The JAMA's forecast of 200 to 300 millimeters by noon June 3rd represents the agency's best estimate of how much of that moisture the front will convert to rainfall over the forecast zone. The 2018 totals in the worst affected areas reached 250 to 400 millimeters in specific catchment locations. The current forecast falls at the lower end of that range. Whether the actual delivery matches, exceeds, or falls short of the forecast is the question the post-event assessment will answer. The geography that took the worst of the 2018 damage was not coastal. It was inland and mountainous. The river valleys above the cities of Hiroshima and Okinawa. The hillside neighborhoods that had been built over decades into terrain that the original land use planning had treated as marginal but acceptable for residential development. The reservoirs that had been engineered for normal Baiu rainfall, but that filled to capacity within hours of the amplified rainfall arriving. The drainage systems that had been calibrated against historical rainfall maxima from the 1980s and 1990s, and that were now operating against a new climate state with measurably higher rainfall maxima. The satellite record from the TRAR-MM and GPM instruments, the Tropical Rainfall Measuring Mission, and the Global Precipitation Measurement Mission provided continuous rainfall observations along this seasonal front over a 23-year study period. That dataset shows heavy precipitation frequency along the front increased 24% in the decade ending 2019 compared to the prior decade. 24%. That number comes from direct measurement, not modelling. The satellite counted how often heavy rainfall events occurred and compared one decade to the next. The primary driver of the increase, according to the dataset, is enhanced water vapour transport from the Pacific. That phrase, enhanced water vapour transport, translates to more tropical moisture is reaching the front more often than it used to. The mechanism that transports the moisture is the same mechanism we have been describing throughout this video. Pacific tropical systems pushing moisture north into a stalled front. The pattern intensifies when a typhoon is present to the south. The measurement confirms what the mechanism predicts. The combination of a loaded seasonal front and a typhoon's moisture field produces rainfall totals that neither system could approach independently. What the 2018 evidence says about the current trajectory is direct and specific. Let me lay out each comparison point in sequence. The Baiu front in 2018 was in the same seasonal position it occupies right now in 2026. Early to mid-Baiu season, the front sitting in its typical east-west orientation across central and western Japan, the continental high pressure to the north holding the front in place. These are not coincidental matches. They are the standard configuration that the Baiu season produces in early June through early July of every year. The 2018 event was not an aberration in front position. It was the standard front position interacting with a tropical system. The triggering storm in 2018 was weaker than Jangmi. Praparoon at its peak had central pressure around 965 hectopascals. Jangmi at its peak had central pressure around 975 hectopascals. Different storms have different intensity profiles, but both fall within the Category 1 to mid-Category 2 range. Neither was a super typhoon. Neither produced the kind of headline-grabbing wind speeds that draw maximum international attention. Both produced the moisture field necessary to amplify a stalled Baiu front to catastrophic delivery rates. The wind strength of the typhoon, in the context of typhoon-Baiu front interaction, is largely irrelevant. What matters is the volume of moisture in the outer circulation and the proximity of that circulation to the stalled front. The soil saturation level in the affected regions in 2018 reflected the same weeks-long Baiu season rainfall pattern now documented across Japan in June 2026. The 2018 event hit in early July, slightly later in the Baiu season than the current event. The ground had been absorbing front rainfall for approximately 5 weeks by the time the amplified rainfall arrived. In the current 2026 event, the front has been active over Japan for approximately 3 weeks. The absolute amount of preloaded moisture in the soil is somewhat lower in 2026 than it was in 2018, at the equivalent moment. That difference may matter. It may not. The threshold for slope failure depends on more than the absolute moisture level, and the incoming rainfall load is the dominant factor in determining whether the threshold is crossed. The JMARS rainfall forecast for June 3, 2026 of 200 to 300 millimeters for western and central Japan is consistent with the rainfall rates that preceded the deadliest phase of the 2018 floods. In 2018, peak 24-hour rainfall totals in the worst affected prefectures reached 250 to 400 millimeters in some catchment areas. The current forecast falls within the lower end of that range. If actual rainfall matches the forecast, the event will sit in the range of the 2018 precedent. If actual rainfall exceeds the forecast, as sometimes happens when models underestimate the front amplification, the event could approach 2018 totals in specific catchment areas. If actual rainfall falls short of the forecast, the event will be a serious flood event without 2018 scale casualties. The storm was never what you needed to survive. The current configuration does not guarantee a 2018 level outcome. It matches the conditions that produced one. That distinction is critical. The mechanism is the same. The historical precedent is documented. The contingent factors that determine the exact severity of any specific event remain difficult to predict in advance. The agencies issuing the warnings are operating with the knowledge that the conditions are present for a high-end outcome, and the uncertainty that the high-end outcome is not guaranteed. They issue the warning at the level appropriate to the worst plausible case. That is the conservative approach. It is the correct approach when the mechanism is confirmed active. The 24% increase in heavy precipitation frequency, documented by the Japanese research team, was measured before the 2026 Pacific season began, before El Niño conditions started developing in the Pacific, and before Jangmi formed. The trend they were measuring was the baseline. What is happening right now may sit above it. The Pacific sea surface temperatures driving the 2026 typhoon season are running warmer than the average of the 2009 to 2019 reference decade. Warmer Pacific surface temperatures mean more moisture available to tropical systems. More moisture in tropical systems means stronger moisture injection into the Baiu front when those systems approach Japan. The trend documented by the researchers may already be obsolete as a forecasting baseline. The economic damage from the 2018 event, $9,086 billion, represents the cost of cleanup, infrastructure rebuilding, agricultural losses, and direct property damage in the affected prefectures. That number does not include the long-tail costs, the multi-year impact on insurance markets, the cost of revised disaster prevention infrastructure that the government built in response, the cost of relocating residents from areas determined to be permanently uninhabitable after the slide damage, and the macroeconomic impact of the disruption to industrial supply chains based in the affected regions. The full economic footprint of the 2018 event extended well beyond the headline damage figure and continued to be paid in the years that followed. The next data update is the JMAR post-landfall impact assessment, expected within 12 to 24 hours of Jangmi clearing the main islands, approximately June 3rd to 4th, 2026. That assessment will confirm actual rainfall totals against the forecast and document whether the Baiu front amplification matched the 2018 pattern in scale. It will also include preliminary damage reports from the prefectures in the forecast zone. That is the specific data point that changes everything we currently know about whether the warning matched the event. Until that assessment is released, the current forecast remains the best available description of what is happening. After it is released, we will know how well that forecast captured the reality. The JMAR post-event assessment draws on the densest network of ground-based weather instrumentation in the world. Japan operates approximately 1,300 automated surface observation stations nationwide, known as Amadas stations, each recording temperature, precipitation, wind, and in many cases soil moisture at 10-minute intervals. Those 1,300 stations are supplemented by 20,000 rainfall gauges operated by local governments and river management authorities across every prefecture. Every one of those instruments was recording through the June 3rd event window. The post-event assessment will aggregate those records into the most comprehensive picture of where the rain fell, at what rate, and for how long. That data resolution matters for a specific reason. The difference between a 2018 level event and a serious but manageable flood event is not visible in the regional forecast numbers. Both scenarios are consistent with a 200 to 300 mm regional forecast. The difference shows up in the hourly rate data from specific catchment stations. In 2018, certain stations in the Hiroshima Mountains recorded rainfall rates above 100 mm in a single hour during the peak delivery window. That rate, sustained for 2 to 3 consecutive hours, is what turns a slope that was holding at elevated soil moisture into a slope that fails. The Amadas network will have captured whether June 3rd produced those peak hourly rates in the most vulnerable catchment areas, or whether the rainfall was distributed more evenly across time, in a way that the drainage systems and slopes could absorb without failure. The other critical data the assessment provides is the before and after river level record. For each river system in the forecast zone, the JMAR will document the level at which the event began, the level it reached, how quickly it rose, and whether it exceeded flood advisory thresholds. That progression tells the full story of how the accumulated soil saturation from 3 weeks of Baiu season rainfall combined with the additional front-amplified input to determine whether each river system stayed within bounds or moved outside them. Those records are what disaster prevention engineers use to evaluate whether the current infrastructure is adequate for the new climate state the satellite data has documented, or whether the next investment cycle needs to begin. The 2018 numbers are the historical proof of what this mechanism produces. In part 6, we are going to answer the question this entire video has been building toward. What does all of this mean for the 37 million people in Tokyo right now? For the American families stationed at Yokosuka Naval Base, and for anyone watching this from the United States as the Pacific becomes more active every season. Part 6. What comes for you? And that brings us to the thing this whole story has been building toward. The mechanism has a name. The 2018 evidence is on the record. The current configuration has been confirmed by the JAMA in its own advisory language. What remains is the question that matters most for anyone watching this video. What does it mean for you, for the people you know, and for the country whose bases and families are positioned directly in the path of the system that is active right now? The Kanto region, which includes Tokyo and the surrounding metropolitan area, has a population of 37 million people. 37 million. That is a population larger than the state of California, compressed into a coastal plain and surrounding hill country roughly the size of Connecticut. The JMAR forecast 200 millimeters of rainfall for this region by noon on June 3rd. 200 millimeters in plain American measurement is just under 8 inches of rain. 8 inches falling over the most densely populated metropolitan area in the developed world, on top of weeks of pre-existing Baiu saturation in under 24 hours. Yokosuka Naval Base, the home port of the United States 7th Fleet, is located on the southern coast of Kanagawa Prefecture, directly in the Kanto region. As of June 2nd, Yokosuka had raised its tropical cyclone condition of readiness to level 2. Tropical cyclone condition of readiness 2 means destructive winds of 58 miles per hour or greater are anticipated within 24 hours. Base schools were closed for Wednesday. Non-essential personnel were directed to shelter. The US Navy's largest installation in Asia was in preparation posture for a storm that, by every headline metric, was weakening and moving fast. Picture a Navy spouse at Yokosuka, whose husband is deployed aboard a ship currently at sea. She has 2 children in base school. On the night of June 2nd, she received notification that school is cancelled Wednesday. She checked the forecast and saw a weakening typhoon. She saw the storm's track moving northeast, away from her base's position. She made a decision to shelter in place rather than evacuate to higher ground. She made that decision based on everything she knew about how typhoons work. What she did not know on June 2nd is the same thing the retired schoolteacher on Shikoku did not know, that the 200 millimeters of rain forecast for her prefecture was not coming from the storm she was watching on the map. It was already positioned above her, being fed from below, and the fact that the storm was weakening had nothing to do with when or whether it would arrive. The 7th Fleet's Carrier Strike Group is headquartered at Yokosuka. It is the primary instrument of American military power projection in the Western Pacific. Flood damage to that base does not resolve in days. Naval infrastructure repair after significant flood events historically runs 6 to 18 months for full restoration. During that window, ships deploy from alternative positions. Maintenance schedules compress. American military capability in the Pacific operates at reduced capacity for as long as the base is damaged. That is the operational consequence of a flood event at Yokosuka. It is not a domestic story, it is a national security story. The families of American service members stationed at Yokosuka, Atsugi and Zama live in communities along the Kanto coast and in the river valleys that the JMAR's 200mm forecast covers directly. Yokosuka itself sits on the Miura Peninsula, a hilly coastal landform extending south from the Kanto Plain. The peninsula has both flat coastal sections that face surge and flood risk and elevated interior sections that face landslide risk in saturated rainfall events. Atsugi sits inland, on the Sagami River plain, vulnerable to riverine flooding. Zama, also inland, sits in lower-lying terrain that has historically experienced flash flooding during heavy rainfall events in the Kanto region. The military housing distributions across these three installations place American families across the full range of flood and landslide exposure profiles. The JMARS post-event assessment window opens within 12 to 24 hours of Jangmi clearing Honshu, approximately June 3rd to 4th. That assessment will provide the first official confirmation of whether actual rainfall totals match the forecast range. The assessment is generated by the agency's network of automated weather observation stations distributed across every prefecture, supplemented by the satellite-based precipitation observations and the local prefecture-level rainfall reports. The assessment will contain rainfall totals by observation station, regional aggregates, and a comparison against the original forecast. It will be the first complete picture of what the front actually delivered. If those totals match the forecast, the damage reports from 15 to 20 prefectures will follow within 24 to 48 hours. The prefectural disaster response agencies generate preliminary damage assessments using local government inspectors, fire department reports, police reports, and self-defense force reconnaissance. Those preliminary reports cover residential damage, infrastructure damage, casualty counts, evacuation populations, and the operational status of essential services. The reports are preliminary and subject to revision as access to affected areas improves over the days following the event. The initial 24 to 48 hour reports historically capture the headline scale damage but undercount the long-tail damage that emerges over the following weeks. If the Baiu front amplification matched or exceeded the 2018 pattern, the preliminary reports will begin to surface during that same window. The initial markers of a 2018 scale event will include casualty reports from mountain prefectures with active landslide zones, infrastructure damage reports from major river systems with documented overtopping, and evacuation population numbers in the hundreds of thousands to low millions. The pattern that distinguishes a Typhoon Baiu front interaction event from a routine typhoon flood event is geographic. Routine typhoon flood events concentrate damage near the landfall area. Typhoon Baiu front interaction events distribute damage across the full corridor where the front was active, often with the most severe damage occurring well away from the typhoon's actual track. This is not a story that resolves when the typhoon moves offshore. It resolves when the front exhausts itself and the rain stops. That may take another day or two after Jangmi has passed. The front does not respect the typhoon's schedule. The moisture injection continues as long as the typhoon's outer circulation remains within range. After the typhoon moves out of range, the front loses its moisture amplification and reverts toward normal Baiu rainfall rates. The transition is not instantaneous. The front has the moisture already entrained. That moisture continues to fall until the front clears it. The tail of the event extends beyond the typhoon's departure by a window measured in tens of hours, not in hours alone. Two scenarios are possible from this point. In the first, the Baiu front delivers the forecast 200 to 300 millimeters, but the soil saturation and slope conditions in the most vulnerable areas hold below catastrophic threshold. Significant flooding and some landslides occur. Infrastructure damage is documented but manageable. Evacuation orders prove precautionary in the sense that the worst-case slope failures do not occur. The system produces a serious event that validates the warning without matching 2018's death toll. The post-event assessment confirms a Typhoon Baiu front interaction event of moderate severity, and the warning system performance is evaluated as appropriate to the threat level. In the second scenario, the front amplification exceeds the forecast range. Soil saturation in the most vulnerable mountain prefectures reaches the critical threshold documented in 2018, and cascading landslide events begin in the river valleys above populated areas. The warning was accurate. The precision was not. The casualties arrive in the gap between those two things. The geography of the worst damage will not be predictable in advance because the specific catchments that fail depend on factors below the resolution of the forecast models. The post-event assessment in this scenario documents an event in the range of the 2018 precedent, and the warning system performance is evaluated as appropriate to the threat level, even though some casualties occurred. The storm was never what you needed to survive. The JMA post-landfall impact assessment is the specific data point that resolves the two-scenario uncertainty. It will be released within 12 to 24 hours of the storm clearing Honshu. It will contain actual rainfall totals by prefecture, preliminary damage reports, and the official classification of the event relative to historical precedent. If the totals match 2018, the disaster response will escalate immediately. If they fall short, the warning will be assessed against the outcome. Either result tells us something specific about how well the current forecast models captured the Typhoon Baiu front interaction in real time in 2026. What changes after the assessment is not just the historical record for this event. What changes is the calibration data available to every forecaster in the world who tracks Pacific typhoon front interactions. Each time this mechanism produces a documented event with confirmed rainfall totals, confirmed damage geography, and confirmed casualty distribution, the forecast models get a new data point to calibrate against. The 2018 floods produced a generation of improved model parameters for front amplification events in the Western Pacific. The 2026 event, whatever its final severity, will produce the next generation. That calibration process has a direct consequence for American viewers whose weather is downstream of the Pacific system. NOAA's seasonal outlook models, the atmospheric river forecast tools that protect California from flooding, and the Gulf moisture surge tracking that protects the Louisiana and Texas coast all incorporate the same basic Pacific moisture front interaction physics that the JMAR is applying to Jangmi right now. When the Pacific models improve their handling of typhoon front interaction, the downstream American models improve as well. The science is connected. The data from tonight feeds into the forecast that protects an American city in a future storm season. There are 37 million people in the Kanto region waiting for this front to clear. There are 50,000 American service members and their families distributed across bases from Okinawa to Yokosuka to Zama to Atsugi, all of them inside the forecast zone of a warning issued in technical language that the international coverage never fully translated. The mechanism has a name now. The name explains the warning. The warning explains the numbers. And the numbers, when the post-event assessment releases them, will tell us whether the warning system caught this one before it became the next 2018. The data point that resolves the two-scenario uncertainty is already being generated. The JMA's monitoring systems are recording rainfall totals in real time. The number that tells us which scenario this is will be public within 24 hours, and that number will either confirm that this warning system works or reveal exactly where the gap between forecast and consequence lives in the data. For American viewers, the relevance extends beyond the immediate event. The Pacific Basin is the primary tropical cyclone basin, affecting both East Asia and, on a longer trajectory, the western coast of North America. Pacific sea surface temperatures are the dominant input to tropical cyclone formation across the entire basin. The same warming that is enhancing moisture transport into the Baiu front is also affecting the moisture availability for storms that reach the Hawaiian Islands. The storms that send moisture plumes into the Pacific Northwest as atmospheric rivers, and the El Niño-related precipitation patterns that affect California and the southwestern United States in winter. The mechanism documented over Japan is one expression of a broader Pacific moisture cycle that affects American weather on multiple timescales. For viewers in the continental United States, this mechanism has a direct domestic parallel that most Americans have experienced without knowing its name. The United States Gulf of Mexico plays the same role for the American Southeast and Mississippi Valley that the warm Pacific plays for Japan. When a tropical system or strong low-pressure system pushes Gulf moisture northward into a quasi-stationary frontal boundary over the Central Plains or the Mid-South, the result is the same as what is happening over Japan right now. Extreme rainfall distributed over a wide corridor rather than concentrated at a single storm center, delivered to already saturated ground, persisting long after the triggering system has moved on. The 2016 Louisiana floods produced 13 deaths and $10 billion in damage without a named hurricane making landfall anywhere in Louisiana. A slow-moving weather system pushed Gulf moisture into a stalled frontal boundary over southern Louisiana. The front locked. The rainfall rates reached historic levels in the Baton Rouge metro area. The event produced more than 31 inches of rain in some locations over 72 hours. More than 100,000 homes were damaged. The triggering system was never a category anything. It had no name. It received no major international coverage until the damage reports started arriving. The mechanism was the same as what the JMAR is warning about in Japan right now. The American version did not have a name in the coverage either. The July 2023 Vermont floods that paralyzed the state and damaged or destroyed hundreds of homes and miles of road were produced by the same dynamic. Moisture from the remnants of a tropical system feeding into a stationary frontal boundary over the northeast. Vermont received nearly 2 inches of rain per hour in some locations, more rainfall in a single day than any previously recorded July event in the state history. The Winooski, Mad and White rivers crested at record or near-record levels within hours. The damage to Vermont road infrastructure alone exceeded $400 million. That event happened in the United States, in a state that most Americans think of as pleasant and green in summer, from a mechanism that the weather coverage described as simply heavy rain from a slow-moving system. The mechanism operating over Japan right now is not a distant phenomenon specific to East Asia. It is a version of the same moisture front interaction that has produced multiple billion-dollar flood events in the United States in the last decade. The El Niño conditions developing in the Pacific in 2026 are expected to continue affecting global weather patterns through the rest of the year. The Pacific storm activity for the remainder of the typhoon season, June through November, will be measured against the historical baseline for El Niño years. Active El Niño seasons produce different storm tracks than neutral or La Niña seasons. The interaction of those tracks with the Baiu and Baiu front systems will determine whether the rest of the 2026 season produces additional Typhoon Baiu front interaction events at the upper end of the historical severity range, or whether the current event is the season's primary occurrence. The post-landfall assessment is the next milestone. Beyond it, the JMAR will issue a full post-event analysis within several weeks that compares the 2026 event in detail against the 2018 precedent and other historical comparisons. That analysis will inform the next round of disaster prevention infrastructure planning, the next round of forecast model refinement, and the next round of public communication about the Typhoon Baiu front interaction mechanism. Each major event in this category, when properly analysed, improves the science. The science is moving. The mechanism is becoming better understood. The communication gap is the remaining frontier. The story does not end when Jangmi clears Honshu. The mechanism that produced the catastrophic rainfall in 2018 does not stop when the storm passes. The Baiu front continues delivering rain for hours after the typhoon that fed it has moved offshore. The JMAR confirmed this in its advisory. The front was active before Jangmi arrived. It will remain active after Jangmi leaves. The post-event assessment is the only document that will tell us the final rainfall totals and whether the amplification matched the 2018 pattern. That document will be released within 12 to 24 hours. When it is released, we will have the specific answer to the specific question this video raised. Did Typhoon Baiu front interaction produce a 2018 level event in 2026? Or did the front hold below catastrophic threshold? That answer matters not just for the people currently in the Kanto region and western Japan. It matters for understanding how well the current warning system performs when this mechanism is active. It matters for the next time. And based on the documented 24% increase in heavy precipitation frequency along this front over the last 2 decades, and the developing El Niño conditions that are expected to continue warming Western Pacific surface temperatures through the rest of 2026, there will be a next time. The JMAR's post-landfall impact assessment is the next data point. We will be tracking it as it comes in. Every rainfall total released by station every preliminary damage report from every prefecture in the warning zone. Every comparison to 2018, the agency draws in its own analysis. The data is coming. We will be reading it as it arrives. You will be the first to know when it does. Subscribe to Rupture because the JAMA's post-landfall impact assessment releases within 24 hours, and we will have those rainfall totals, the preliminary damage reports, and the comparison to 2018 the moment they are confirmed. That data either validates this warning or reshapes what we know about how the forecast models handle Typhoon Baiu front interaction in real time. You will want to know which one it is. If this video changed how you understand what a weakening typhoon can actually do, leave a comment below. Tell us, did you know the rain was coming from the front before you watched this? The answer to that question is the measure of how well the international weather coverage is serving viewers who depend on it for their understanding of how these events actually work. We read every comment. We use what you tell us to shape how we cover the next one. The Japan Meteorological Agency's damage numbers are coming in right now. That data either confirms this was another 2018 or tells us the front held back. Either way, you will want to know which one it was.